Where did we stop in the last class? Where did we stop? Types of energy units in different energy units, right? Sure. Potential and kinetic, right? So we are defining work, all positive, negative work. So I think we have covered the first part of this chapter. Right? Okay. So I'm starting with the second chapter, the second part of the chapter, which is basically about mechanical energy. So what is mechanical energy? Mechanical energy consists of the sum of kinetic energy and potential energy. Okay. So we say E is equal to A plus U. What is the mechanical energy of a body? Sum of its kinetic and potential energy. So potential energy is represented by letter U, kinetic as A. Right. So we have to derive the expression for potential energy and kinetic energy first. So there are two types of potential energies. Which are they?
Gravitational and plastic.
Right. So expression for gravitational potential energy first. Potential energy types. This we I think briefly discussed. Right. So first is gravitational potential energy. So what is the expression for it? Expression, we derive the expression for. Okay, let's write it separately. First is gravitational potential energy. Second is elastic potential energy. Right? Write it over here. Elastic potential energy. So what is the difference between the two that I had already explained? What is the difference between the two? This depends on the state of rest, or it depends on position, right? Depends on position of the body. State of position of the body. And what about elastic potential energy? It depends on configuration. Change of shape or configuration. Depends on the change of configuration. So whenever the body's shape changes, it develops potential energy, right? And then the external force which is causing the change of shape or deformation, when the external force is released, then it is converted into kinetic energy. Okay? So we'll understand that in detail. So first, we are going to do derivation for expression of gravitational potential energy. Okay, this is what we will do. So for that, this is R. Right? So we consider a body which is kept here. Let us say its mass is m. Now this body is lifted to a height h. Right? So how much force you must have applied on the body? At least you must have applied equal to its weight. Force and resistance. Okay. And it is raised to a height h. So what is the potential energy? So this work done on the body will be stored as its potential energy. Right? So what is gravitational potential energy? Therefore, work done in raising the body by a height h is stored in the body as its potential energy. Because I told you, work energy are equivalent, right? So when I do work on the body, that work will be stored in the body as its potential energy, right? So therefore, U is equal to work done. Work done is force into displacement. Right? What is work done? Force into displacement. Displacement is h. But what is F? mg. So h. Therefore, what is the expression for potential energy? This is the expression for gravitational potential. So any difficulty? So work and displacement are in the same direction, therefore it is positive. Yeah. So can anybody tell me what is the value of mu at the ground? That is 0. So U at Earth surface will be 0, and U over here will be mg. This you have to do. So sometimes I miss this on, etc. Okay, I just go ahead. Fill in, huh? Just fill in those missing ones. Depends on the change of configuration or shape of the body. Now I remember I had given it removed. When I removed the net, then okay. So this potential energy will be as long as the body is held there with the force. And the moment you remove the external force, it will turn into magnetic energy because now it has motion. Huh? Okay. Then here is the left side of the ball. Okay. So now what is elastic potential energy? This is just a theoretical discussion. So we'll understand it with the help of example, right? So examples of elastic potential energy. So one is in the compressed spring. So first is compressed spring. Let us say this is the natural the ball is kept here. So this is a relaxed spring. So what happens is, pay attention here. Are you writing that or this? This side. Okay, you must complete it. Okay, stretched bow. Right. Shall I begin the explanation?
Yes.
Okay. So, what is elastic behavior? Elastic behavior is, when do we say that the body is elastic, right? So under the influence of some external force, its shape will be changed, right? But when the external force is removed, it tries to regain its original shape. So this is the natural relaxed state of the spring when a ball is kept and it is compressed down, right? So what it will have is some work is done, right? So some force was applied here in the downward direction, and there is some displacement also, right? So whatever work is done, right, that is stored as potential energy in the spring, correct? Now when this finger is released, so what will happen? It will suddenly try to gain its original shape. In that, it will apply a force. Now work will be done by the spring, and therefore this body will set into motion. So what will happen? This potential energy of the spring, right? So what happens is potential energy, elastic potential energy stored in the spring, in the compressed spring, right? When released, appears as the kinetic energy of the ball. Got it? So this ball will fly. The moment you release the spring, ball will fly. Understood? So where will ball get energy from? Potential energy of the spring. Likewise, so this is the relaxed position of the bow string. So this is the string of the bow, right? So when it is, so initially it will be like, right? But when it is stretched, then elastic potential energy will be stored in the string. And when you release it, it will try to regain its original position, original shape. So that will appear. So when the stretched string is left, the potential energy of the stretched string will be given to the arrow. No, bow is this arrow. Then the kinetic energy of the bow, potential energy stored in the bow will be transferred as a kinetic energy of the arrow. Got it? So from where this arrow is flying, so this is the principle on which revolver or the bullet is fired. So in the gun, when the bullet is loaded, it is, you must have seen, when the cartridge is loaded, it is stretched behind. The trigger is pulled behind. Now when you release the trigger, that's when the bullet fires. Okay? So that's the potential energy of the spring at play. Right? So here also, when the string is released, the elastic potential energy of the string shows up as kinetic energy of arrow. So like that, there could be many examples, right? So what we just witnessed is the one form of energy is getting converted into other form of energy. So we are saying energy conversion. Okay, so energy is coming from us, right? So it's not created; it's coming from us when we work. That energy went into string. When we release, that potential energy went into arrow as its kinetic energy, right? So we are not creating any energy, we are just spending it or transforming it from one form to other. So when I work like this, which energy got spent? Chemical. What energy I have? Calories, right? Chemical. So then my muscular, so many things are happening. Chemical is causing my muscular energy, and then that is basically mechanical only, right? And it's potential energy, then it's kinetic. All that. Okay. So I think I mixed up some topics here. This is basically after that I should have derived the expression for kinetic energy. But anyway, this is conversion of potential energy to kinetic energy. Okay. One form energy getting converted into other form of energy. That's desired example. Getting converted into. Or in the same title, you can write getting converted into kinetic energy. Converted into kinetic energy. Okay. It is that example. So you can read it. Right. So if can I ask one question here if you are done writing? So if you are not getting the diagram right, it is okay, right? With some practice you will get it. Yes, as long as you got the message, it is okay. Any other question? So suppose this height was h1, right? Now I am further raising it by another height h2. Question is, what is the change in potential energy in lifting this body from height 1 to height 2? So till here it has mgh1 now, for example. Right? So what is the gain? Obviously, potential energy will increase because the height is increased. So what is the gain in potential energy when the body is further lifted by h2? mgh2 only?
mg brackets h2 minus h1.
So what is the total height from here to here? Total height is h1 plus h2. So at the top position, right? So what is the energy difference at top position? I am saying P2 is equal to, or U2, let's say U2 is equal to mg h1 plus h2. See, the way the question is asked, I am giving you height is h2 from here to here. Then it is different. If I said if height h2 is from the ground, then answer will be different. Okay, so you have to be reading it carefully. h2 is only from here to here. What is the total height? h1 plus h2. What is u1? mg(h1). Right, so what is the gain? Therefore, delta u, which is more, u2 minus u1. how much it is? mg h1 plus h2 minus mg h2 minus mg h1. What it will be? It will be only mg h2. This is only gain. Okay, in this case. If I would have asked the question in this way, that the full height is h2 and this is h1, then it will be mg h2 minus h2, like the way it is given in the book. Okay. So do you want me to convert it in the way it is asked in the book, or this is also okay? Have you got the concept? This is okay, right? Yeah, because I have changed it. Okay. So you're going to. The bow and arrow example is also from your book only, but they are not drawn. So anybody has any question? Please feel free to ask if you have any question. So in derivation for expression of potential energy, we have used the fact is work and energy are similar. So whatever is the work done, that is appearing as the potential energy, right? Same concept we use for deriving expression for kinetic energy. Can I erase this now? So what are the two types of mechanical energy?
potential and kinetic.
Okay. So derivation of expression for kinetic energy. Now, I think we have defined already what is kinetic energy. Energy by virtue of its motion, right? So how will we derive this expression? So suppose there is a moving body, right? Whatever work I do in stopping that body, that should be a measure of its kinetic energy, right? So I have to do some work in stopping the moving body. So whatever work I am doing must be equal to the kinetic energy in the body, correct? So that's the logic I will use here. Kinetic energy of a body is equal to work done in stopping it. Right? So let me draw this scenario over here. Suppose this was a body of mass m. Let us say it was initially moving with velocity v in this direction. Right? It is moving in this direction. Now I applied a force in opposite direction. That's a moving body. But will it stop suddenly? No. So it will keep moving And let us say after traveling a distance s, it finally stops. Right? So it stops here. So I'll take the distance from the center. I told you every body is a point body for me, right? So I'll measure the distance from the center. Is the scenario understood? So what is the initial velocity? Initial velocity is v. And what is the final velocity? Final velocity is 0 when the body stops. Stop. So whatever work is done by me in stopping this body, right? That should be the measure of its kinetic energy, right? So therefore, kinetic energy is equal to force into displacement. Now force is in this direction. Where is the displacement? Opposite direction. So that's as cos of 180, right? Since force and displacement are in opposite direction. Now what is cos 180? Minus 1. So this is minus Fs, right? So far so. Now what is that? Mass into acceleration. Whatever acceleration in the opposite direction. Then what is S? S is equal to, this is how I will calculate. Since V square is equal to U square plus 2AS, right? But what is V? V is 0. What is U? U was, initial velocity was V square, right? Plus 2AS. So therefore, what is S? S is equal to minus V square upon 2A. This is what we do. So be careful. My final velocity is 0. My initial velocity is V, because body was initially moving with velocity V. Be careful. Huh? So this is what, since. So should I write one more as? Should I write or you will pick it up from there? Huh? We'll pick it up from there because in scenario I have explained initial velocity. It is V, right? And final velocity is 0 because body is stopped here. So therefore I will substitute here. So what is my S? Minus V square upon 2A. Okay, from where I have got this. So now this A is cancelled and minus minus is cancelled. What am I left with? Half M V square. So this is the expression for kinetic. Okay, half M V square. derivation of expression for kinetic energy. Now we'll slightly modify it to get the work energy here. Is everyone ready? So what is work energy theorem? Now we are changing the scenario. This body is now moving with some velocity u. Okay, the initial velocity. Its mass is m. And now some force is applied on it for a distance s. Right? Some force is applied on this body while it covers distance s. So what should happen when the force is applied in the direction of displacement? What should happen to its velocity? Increase or decrease?
Increase.
Increase. Because if I am running and somebody pushes me, I run fast, right? So my velocity after traveling distance s will become v now. So whatever is the work done by the force, right? So that work done will appear as the increased kinetic energy of this body. Isn't it? The gain in kinetic energy, like when we lifted the body, there was a gain in potential energy, right? Likewise, when I work on the already running body, then that additional work will appear as its increased kinetic energy, gain in kinetic energy, correct? So that is work energy. Right? So what does this theorem say? States work done on a body is equal to change in its kinetic energy. Right? Work done on a body is equal to change in its kinetic energy. That is W is equal to A final minus A initial. Right? So this is the change in kinetic energy. Right? This must be the change in kinetic. Now let us see. Let's prove. Right? So what is the work done on the body? Work done on the body is equal to force into displacement in this case, because force was applied till this displacement. Now force and displacement are in the same direction, right? So cos 0 is 1, so I am not writing anything, right? And what is S in this case? S in this case, V is V, U is U. So S is equal to V square minus U square upon 2A. Correct? Right? S is V square minus U square upon 2A. So this A cancelled. So what do I have? I have half M V square minus half M U square. But what is this? This must be final kinetic energy, because when the object is moving with velocity v, what is the kinetic energy it has? Half mv square. When the object is moving with velocity u, what is the kinetic energy? Half mu square. Correct? So this is nothing but final kinetic energy, because this is final velocity. And this is initial velocity, so this must be initial kinetic energy. This is how work energy theorem is proved. Any difficulty in understanding? Okay. So whatever work was done, it appears as gain in the kinetic, right? Any questions, anyone? Is everybody done right? So what we'll discuss now is different types of kinetic energy. So we are already familiar with different types of potential energy, gravitational and elastic, right? So what are the different types of kinetic energy? So kinetic energy depends on the motion. So how many types of motions of right? So simplest is straight line motion or translational. So there is translational kinetic energy. Right? So rotational is second and then vibration. So because three types of motions are possible, vibration. So vibrational motion is to and fro motion of an object around its main position, like vibration of atoms. Right? So like if a car is moving, right? So if you treat car as a point object, then car is moving in a straight line, so it has a translational kinetic energy. But what about its wheel? So wheel will have rotational kinetic energy, right? So car and wheel system will have both some of translational and rotational kinetic, right? So see, the wheel motion is, it is rotating around the axis and it is also going forward. So wheel has both, right? So like Earth is revolving around Sun. This is Sun. So Earth is spinning around its axis and it is also translating in the orbit. So it has both translational and rotational kinetic. Okay. So I gave you both examples. Now, what about vibrational kinetic energy? So, like in case of gas, right? Say hydrogen gas or oxygen, right? So during gas, these molecules are traveling. Let us say there is a container. So the molecules will collide and then will rebound, right? So there is a random motion going on. At the same time, they might be spinning, so that is rotational. But O2, like these two oxygen atoms, they might be coming close and going away, like they are vibrating, spinning, and traveling. It's a complicated motion, right? So it might be coming close and going away. So this is a, so while it is doing like this, it's at work. So mostly all the atoms have this kind of complicated behavior. They vibrate, rotate, and travel straight. Okay? Like in case of Earth, if it is like bulging around its axis, then this also will have some vibratory motion. Got it? Like when it is spinning, it will bulge out, right? And if it is spinning less, then it may contract, but it doesn't happen. Its speed of rotation is constant. But imagine there is some object whose speed changes while rotating, so it will expand around the axis. Okay?
The mechanical bell. That's the reason it's vibrating.
Which like I'm not able to visualize. The bell in the school or in the church, like.
That's it. Mechanical bell is there. It vibrates and produces.
So it's produced by any vibrating object, right? But this is like atomic vibration. I mean, we will not get that. At a very microscopic. Anyway, so what you have to remember is vibrational kinetic energy is possessed by any body which is vibrating, like the string of the guitar. Okay. So when it is still, now when you pluck it, so it will start vibrating on both the ends. It has a vibrational energy. It's the motion of the string, right? So it will have vibrational kinetic. Got it? Something like that. So we have discussed types of kinetic. How much more time here? We have 7-8 minutes. Not really. So any questions still here? All the conceptual part is over. Next is conversion of energy from one form to other, right? So different forms of energy we have already covered, right? Like solar energy, heat energy, light energy, right? What is the source? Solar energy, the source is sun. But we cannot use the sun's energy directly, like it's very diffused. But we need concentrated form of energy, right? So we have made actually various devices. Plus and right. So to be able to use energy or harness energy, we have to have some devices. Like what solar devices you have? Solar panel, then solar furnace, then solar cell. So solar cooker is like furnace is different, cooker is different. So there could be any number of applications that you can think of. So this is like theory, so you will read and understand. And what about heat energy? How do we produce heat energy? By burning anything. So how heat energy is produced? When we burn, what is the stored form of energy? Chemical. Like when we burn any fuel, the chemical energy stored in the fuel is converted into heat. And when you burn anything, it also produces light. Light energy. What does light energy let us do? It lets us see things, right? Light energy helps us see things. What is the source? Sun, and artificially produced light in bulbs, etc. Okay. What is chemical energy? So chemical energy is energy which is stored inside fossil fuel, right? Coal, petroleum, right? Also, it's stored in the form of calories. When we eat food, right? The energy stored inside plant through photosynthesis is also chemical energy. So stored energy in living things is chemical energy. What is hydro energy? Hydro is water. So any water which is moving. So the energy possessed by moving water is its kinetic energy basically, which is called hydro energy. Where do we use that energy?
Producing electricity.
For producing electricity. So in the dam when we store, it has a lot of potential energy, but it is held back. When we open the gates, then it will flow with a very high speed. So it will have a hydro energy. That hydro energy will rotate the turbine. That turbine will rotate the coil of the generator. So electricity will be produced. The moment coil of the generator is rotated, then electricity will be produced. And electricity produced by hydro energy is called idle electricity. Okay. So the type of electricity produced depends upon how we are rotating the coil. So in this case, the mechanical energy of the water is rotating the coil. So it's called idle electricity. Okay. In nuclear power plant, what we will do? We'll carry out nuclear reaction. So nuclear reaction produces a lot of heat. We will use that heat to boil water and produce a lot of steam. Now steam has a lot of energy, right? You must have seen in a pressure cooker when the vessel comes up. Or in old days, we used to have steam engines. You might witness it in old movies or museums, right? So coal was burned, then water was heated, it was converted into steam. That steam energy was converted into mechanical energy of the steam. So that steam engine can rotate the turbine or the coil. Then we call the electricity as what kind of electricity? It is called as thermally produced electricity or thermal power plant. You must have heard about nuclear plant, thermal plant, idle plant. So only difference is in how we rotate the coil, using which source of energy. Okay. So now it says electrical energy itself. What is electrical energy? What is electrical energy? Yeah. So the energy or the electrified bodies or charged bodies have electrical energy in it. So how do we create charged body? By rubbing them. Okay. So scientists have conducted experiments on various pairs of bodies, like glass rods with silk cloth, plastic with fur. Okay. So when such bodies are rubbed together, opposite charges are developed on them. So what is charge development? See, basically, if you take this pen, okay, it is charge neutral. It's not attracting anything, right? So that means it has equal number of positive and negative charges. Now, if I rub it on my hand, right? So some of the negative charges will get transferred from one body to other. Now a charge difference is created. So if it loses electron, its negative charge has reduced, which means it will become positively charged. My hand has gained electron, so hand has become negatively charged. So positive charge, negative charge. So now if I try to bring it close to any metal piece or any other charged body, there will be force of attraction or repulsion, depending upon what is the nature of charge. That attraction is electric behavior, it's not magnetic. So that's why electrical energy is different than magnetic energy. Got it? So magnet will attract piece of metals. Okay, so that attraction is magnetic attraction, and electric attraction is between electrically charged bodies. Okay, so anyway, so we go slow on that. Then what is nuclear energy? So nuclear energy is basically Einstein gave one formula that E is equal to mc square. Right? Like mass itself can be thought of as energy. Right? So there are nuclear phenomena like fission and fusion. Maybe I think we'll discuss in the next class and fusion. Right? So fusion. In this case, one big nucleus is broken into two small nucleus. Spelling color again. Right? Fission is one big nucleus is broken into two small nucleus. So वो जो दो small nucleus आते हैं ना, from one big nucleus, their combined mass is less than the big nucleus का mass. What did I say? M1 plus मतलब 2m plus m is less than this. So that mass difference is converted into energy as per this law. So whenever the process of fission takes place, the reduced mass appears as heat energy. Okay, in a nuclear reactor we can cause this reaction, fission reaction. Okay. Fusion में क्या करते हैं? Two lighter nuclei are fused into bigger nuclei. Now the mass of the new nucleus is less than the combined mass of the fusing nucleus. So again there is a mass difference. Always the final nucleus mass is less than the original nucleus. So that mass difference appears as energy. So in sun, right? What is the cause of source of energy inside sun? The hydrogen nucleus, two hydrogen nucleus fuse to make one helium atom. Okay, and in that process, a lot of energy is created. So all the sun and stars, their source of cause of energy is fusion. Okay, that's I think in the next class. So this theory becomes little boring, right? I mean, is it boring or was it okay? Okay, chalo, see you in the next class.